All right. Well, how is everyone today?
Very exhausted. I'm glad that this is the last week of my FBS finals.
Yay. All right. Well, yeah. So this is week 10. This is our last week. So my plan for today is to talk a little more about Turing machines. Finish up that conversation. Talk about some aspects of computing. And some questions about what we can or cannot potentially compute with a Turing machine, or with any computer for that matter. And kind of wrap up the material today, and then leave Wednesday strictly for review and talking about the final exam and so on. But let me begin by asking if there's any homework questions. So this is like a double point homework. Yeah, go ahead.
Question about the little cat or the language ones. I was working on the state machine questions, but I have a question about the formatting of the strings. For example, number 3, I'm not sure if that's saying a string that starts with 2 ones plus 10 to the power of n, gives you like 1, 0, 0, 0, or if that's 11 times 10 to the power of n.
It's 2 ones followed by any succession of 1 0 from 0 or more times. So it would be 2 ones. 2 ones, or 2 ones followed by 1 0, or 2 ones followed by 1 0, 1 0, and so on. So all of those.
Oh, in that case, I did number 2 wrong as well.
Okay. So number 2 is just successions of 1 0 where n's bigger than or equal to 0. So that's lambda, or a bunch of 1 zeros, and so on. And number 4, since we're doing this is a 0 followed by 1 to the n. I didn't tell you if n's bigger than or equal to 0 or 1 here, so we'll just go n bigger than or equal to 0. This would be 0, 0, or 0, 1, 0, or 0, 1, 1, 0, or, any number of 1s followed by a 0. And I think those are the only ones where I use that notation. All right, other questions?
Could you do like an example for problem 4 on
Problem 4 on which? On this one or on the counting homework? I don't know which question.
Sorry, I turned off my mic.
Okay.
The counting part of the homework.
The counting part of the homework. Okay, cool. Let me see if I have a direct copy so I don't have to keep going through Canvas. I do not. Okay, so let's... Alright, so question 4. You pick 8 integers from 1 to 10 with no repeats. What's the minimum number of pairs of integers that will add to exactly 11? So anybody got any ideas on this one?
Can I share how I worked through it?
Yeah, or tell us the start of it.
Well, the way I approached the problem was by thinking about how many possible integers could I write before I end up with pair of integers that would sum to 11.
Okay.
So I like split it into 1/2, and I was like, okay, well 1 plus 2 is not going to equal 11. 1 plus 4 is not equal to 11. So probably at the low end, you're going to have a bunch of integers that aren't going to sum to one another. And at the higher end, you're going to have a bunch of integers that aren't going to sum to each other. So I looked for the maximum number of integers that I could find without getting one matching pair.
Okay. Did you end up using the pigeonhole principle in that, or not?
I did.
Okay.
Yeah. So once I found the maximum number of integers that I could pick before I'd end up with a matching pair, I used the pigeonhole principle to say, well, if I have these two sets of integers, one set is full of numbers that will never make a match that equals to 11. The other set of integers is also a set of integers that will never match to make 11. If I add any integer from either set to the other, it will be such that it will create a pair of integers that would equal 11.
Okay.
So I was using sort of that idea of buckets and sort of the different pairs
Okay.
that you could possibly have.
Yeah, cool.
That would equal.
Okay, yeah, so that's basically what I was picturing here. So the hint is, make yourself 5 buckets. And I'm going to label this 110, 29, 38, 47, and 56. And I'm presumably picking unique integers, right? No repeats. And I'm going to put, each integer into its bucket. So if I pick a 7, it'll go in here. If I pick a 3, it'll go in there. And the way I've numbered these buckets, right, if I have 2 integers in here, they add up to 11. And so the minimum number of pairs that will add to 11 is the minimum number of buckets that have at least 2 things in them. So I'm picking 8 numbers, I'm putting them into buckets, and at most I can have 2 things in a bucket. What's the minimum number of buckets that will have at least 2 things in them? And if I only pick 5 integers, I can just go 1, 2, 3, 4, 5. I can have 1 thing in each bucket. But if I'm forced to pick one more integer, then one of these buckets is going to have 2 things. So, if I pick anywhere from 0 to 5 integers, so number of integers I pick, let me pull this out of the way. Number of integers I pick, number of full buckets. If I pick from 0 to 5, so this is guaranteed, number of full buckets. If I pick from 0 to 5, I may not have any buckets that are full. If I pick a 6th integer, I'm guaranteed to have 1 bucket that's full. That's the straight, specific pigeonhole principle. 6 objects, 5 containers. At least 1 container will have at least 2 objects, which means those 2 numbers add up to 11. And now if I toss those 2 numbers out, what have I done? I've picked 4 integers and I have 4 buckets. And if I pick one more integer, then I will have 5 objects going into 4 buckets, right? So that 7th integer is going to give me another bucket that's full. And now if I throw away those 2 elements, I've picked a total of 3 integers and I have 3 buckets. If I pick one more integer, I'm going to have at least 1 bucket with 2 things, so that's going to have me have 3 pairs of integers that add up to 11. So that's using the pigeonhole principle, but sort of doing some other analysis of the problem to put it in terms of putting objects into containers. And then you can try this, right? You can try to pick 8 integers and only have 2 of them add up to 11, and you'll find that that's not doable. else you want to talk about? Please don't wait till office hours for these homework questions, because I think office hours are going to be crazy tomorrow. Because I've got people turning in PA5 late. I've got a bunch of advising people who have said they're going to come by, and the 2 hours is going to go quickly. So if you got any questions about the homework, please ask about them now. This is a good use of class time.
I have a couple of questions, or more questions about the language.
Okay.
Homework. So, number 6, it's not really about solving it, it's just sort of a, number 7. I wrote something, I came up with something for number 7, but it brought a question to my mind about, convention when writing Turing machines.
Okay.
I've noticed that in a lot of them we've written, when the machine is finished, it moves the print head like one space back.
Mm-hmm.
Is that mandatory?
No.
Okay.
No.
When I was working on,
Go ahead.
I would say when I was working on the machine, it ended up with the print head ending on a blank space.
Mm-hmm.
But from the examples we've been working on, it all seemed like the machine would move its print head back one space or something, and I just wasn't sure if that was mandatory, if it was convention, or if it's just all coincidence.
Yeah, I was kind of doing random machine examples last week. The thing is, with a pure Turing machine, every instruction specifies moving the head either left or right. So you do have to move it one way or the other, but it makes no difference. You know, I mean, it makes a difference, but it's totally up to the programmer what they want to do with that final head movement.
Oh, and then my other question.
Yeah.
For number 4, finite state machine that would recognize 1 followed by 0 followed by n number of 1s followed by another 0. How would we approach that such that we can exit the state of checking for n number of 1s and checking for another 0 again?
Well, so we could have a series of states. So we could have, state A, where we're just looking for zeros. So this is our initial state. If we find a 0, we stay in state A. We find a 0, sorry, we're just looking for 1 0. So state A, look for a 0. And if we find a 0, we go into state B. State B, we're looking for a bunch of 1s. So if we're in state B and we find a 1, stay in state B. If we're in state B and we find a 0, then we can go to state C. Look for a 0. If we find a 0, then we move to our recognized state and say, hey, we saw a 0, a bunch of 1s, and a 0. So once you see your first 0, you come to state B. This state I'm thinking of as stay here as long as you're seeing 1s. So if you see a 0, you go straight to C. If you see a bunch of 1s, you stay here, and then eventually you see a 0, go to state C. And so whether you're doing this in software or with flip-flops or in a diagram like this, right, it's helpful to think in your mind, what do I want each state to do? What does it mean when I'm in state B? It means I'm absorbing consecutive 1s. Or some state where I'm waiting for a 0, but I'm going to go back to a bigger state where I'm trying to absorb consecutive 1 zeros, and that kind of thing. Does that make sense?
Yeah, when working on those problems, it seemed like it was a good idea. I'm not sure if it was necessary, but it seemed like it was a good idea to have sort of a garbage state that would catch any sort of excess characters. So, for example, 0 followed by n number of 1s followed by a 0. If it got through all that, and then that last 0 was succeeded by a second trailing 0, then it would be sent to another state in which it would loop back on itself no matter what other characters are given, so that it's not left in the final state.
Mm-hmm.
Or,
Right. Okay, so
is
yeah.
Is it a good idea generally to have that kind of garbage state to catch like strings that are too long or go beyond the match pattern?
So it really depends on the problem, and I didn't specify enough detail in here for you to know exactly what the right thing is to do. So if you do anything that satisfies this, you'll get credit for it. But let's dig into that example. So suppose we want a machine. Suppose we're told, build me a Turing machine that recognizes, a 1 followed by a bunch of pairs of zeros. All right, so we want to recognize 1, 100, 10,000, and so on. So we'll start in some initial state. And if we find a 1, we'll go into a recognized state. And this means we have found this pattern. And if we find a 0, well, now we've seen a 1 followed by an odd number of zeros. But if we see a second 0, then we'll come back here to a recognized state. So this will correctly, take us to this recognized state if we have any of these numbers coming in. A 1 followed by a 0, 0, 0, 0 leaves us in this recognized state. What's not always specified, though, is what to do with unrecognized strings. So for example, suppose we get a string that starts with a 1. Suppose we get a string that starts with a 0, right? All the strings we're going to recognize start with a 1. So if the first character we see in our incoming string is a 0, what should we do? Should we hang out somewhere until we see a 1 and then go on and match? Or should we say, as soon as we see a 0, that you're done, it's not a recognized string, and go to this kind of like catch-all or garbage state? And I didn't specify here. But the difference would be, suppose this is a combination key code entry system on a car or something. And to open your car, you have to type a 1 followed by, 2 zeros. If you type a 0, are you locked out of the car forever? Or if you type a 0 followed by a 1, 0, 0, will the system say, oh, I recognize that 1, 0, 0, and it lets you in? And the answer to that question affects what your machine looks like. So a most general forgiving machine might be something like this. If you type a 0, you just hang out here in this initial state. Once you type a 1, you go to a recognized state. And then if you type a 0, it's unrecognized and the 0 goes back. But a more draconian system might say something like this. If you hit a 0, you go into this bad state. And whether you type a 0 or 1 after that, you're just always stuck in this bad state. And so depending on what the system is supposed to do, you can design your machine accordingly. Now if you did an actual key entry system, you might say you want to recognize something like, a number sign followed by a 1 followed by a succession of double zeros. And so then, our initial state might say something like, if you have, we might start in some state over here and say if you have a number sign, we'll go into our state over here. We're waiting for a 1. If you have a 1, we'll go to a recognized state and look for double zeros. And if you have anything else, we'll just come back to this stage. And if you hit a number sign followed by a 0, we'll go back to this stage and say we're not going to recognize anything you type until you hit a number sign. And now you've got to have a number sign followed by a 1 followed by an even number of zeros. And so most, like key entry systems or keyless entry systems have some kind of character you type at the beginning of your code. That's part of the reason why. All right, other questions? So we're going to do some more TM examples here. What about question 5? What do people think about that?
I said no, because you'd have to have some sort of method to remember the amount of either ones or zeros you have. But I don't think there's a way you can code that into the state memory. I think you can only know what's happening in the current state.
Yes and no. I mean, you're right. Your actions are based, on what's going on in your current state, but you can use the notion of state to implicitly record information about what's happened in the past. And so suppose you do something like this. Here's our initial state. And if I get a 0, I'll go to this state. And if I get a 0, I'll go to this state. And if I get a 0, I'll go to this state. And if I get a 1, I'll come up here. And if I get a 1, I'll come up here. And if I get a 1, I'll come up here. And if I get a 1, I'll go here. And a 1 will go here. And a 1 will go here. And a 0. And a 0. And a 0. And here's my recognized state.
But for an arbitrary length, you need like an arbitrary number of states, and I don't know if that's possible.
That's the hitch right there. So can you design an FSM, a finite state machine? And the reason this is impossible is because of that finite. Now, if you could have an infinite number of states, you can definitely do this. It's very easy. You just keep doing this out forever. But the way this is written, if you input more than 3 ones in a row, right, where is this going to go if you have a 1? Where is this going to go if you have a 0? So to be able to handle an arbitrary length string, you need an arbitrarily large number of states. And that's the trick right there. That's the finite part of a finite state machine. So question, can you write a C program that tells you if you input the same number of 1s and 0s? Suppose you just, do an fgets, read in a 1 or a 0, and you want this machine to tell you after each input whether you've input the same number of 1s and 0s. Can you do that with a C program?
Yes.
Yeah, I mean, you just have a counter for the number of 1s and 0s and see if they're equal. So can a C program do something that a finite state machine cannot? Isn't that what that sort of suggests?
Does this go into the difference between finite state machines and Turing machines?
Well, it would be, except a Turing machine is a finite state machine. So there's potentially a problem here. So how do we do this with a C program? Set a difference equal to 0. If I input a 1, I'll increment my difference. If I input a 0, I'll decrement my difference. So I'll initialize the difference to 0. If I input a 1, I'll increment it. If I input a 0, I'll decrement it. Anytime my difference is 0, I'll say, hey, you've got the same number of 1s and 0s. And I'll just do that in an infinite loop. Does this work? Let me rephrase. Why doesn't this work? Because if this works, then we can do something with C we can't do with an FSM. So why doesn't this work?
Would you need like a different or another if statement that if it's not 0?
Yeah, if diff is not 0, I could print out, not the same. That's okay. But I can definitely add another if statement here. But there's still a reason why this will not work.
I don't know if it's because we wouldn't know where we are in the situational logic.
Expand on
Just my
that.
thoughts.
Yeah, can you expand on that?
I mean, whether or not you've done 2 zeros or 2 1s, you don't know where you are in your little logic graph.
That's true.
I don't know. I was just trying to go a different direction.
Yeah, no, I like that. I like that direction.
Okay.
And I could use 2 counters. I could use 1 counter to count how many 1s, another to count how many 0s, and then if those 2 counts were the same, I could say, hey, I've seen the same number of 1s and 0s. So I could do something like this. Read an input. If it's a 1, increment count 1. If it's a 0, increment count 0. And then see if 1 and 0 are the same. And if they are, print out that they're the same. And go back and read another input bit. So any problems here? Alright, let me ask you another question. How should I declare C1 and C0? What type of variable should I use?
And
I'll make them ints.
Well, but even then, you'd need more of an infinite bucket.
What
'Cause
hap-
You'd end up overflowing an int eventually if you kept it going long enough, right?
Yeah, what if I get 4 billion 1s in a row?
Yeah.
If I start at 0 and I increment an integer 4 billion times, it flips over and it goes back to 0. And after 4 billion 1s, C1 will be 0, C0 will be 0. My program will say, hey, I've seen the same number of 1s and 0s. When in fact I've seen a wildly different number of 1s and 0s. And I could make these long. Or I could make them long. I could make them 128-bit integers. But if I input to the 128th 1s more than I input 0s, they're both going to be equal to 0. So we're still running into a memory issue. We're still running into the fact that this C program has finite memory. In particular, the memory we're using to store an integer is limited, and we cannot count indefinitely high. And so it's truly a finite state machine, even though, you know, we kind of think of it as being unbounded, because for most of what we do, you know, this is a plenty good approximation to infinity, but it's not the same. Just like, you know, I could build a state diagram and I could list, you know, 4 billion states like this and 4 billion states like that, and then it would be doing exactly the same thing as this program. But, you know, the kicker would be that my last state where I don't have another state to go to, I'd just be going back to the beginning where I counted 0 zeros. So that's something to keep in mind as we start moving towards talking about you know, limits of computation and what things can or can't we do with a C program, because, you know, there's definitely limits to what we can do with a finite state machine. There's one example right now, and so that's also a limit to what we can do with a C program. And this is, again, partially why Turing machines were invented 100 years ago, was to study these questions of computability, these questions of what can or can we not do with an algorithm or with a machine that can execute algorithms. Are there bounds on problems that can be solved like this, and if so, what are those bounds? All right, other questions? All right, well, let's keep talking about Turing machines then. And if you remember our setup, Turing machine looked like this: infinite paper tape, so better than a finite state machine, better than a gaming laptop, because it has infinite memory. It's got this read-write head. Our tape is broken into cells, and there's a character, you know, written in each cell, possibly a blank. The tape can be thought of as being initialized to all blanks. And we have instructions of the form, you know, if we have a state and a symbol, then write a new symbol, go to a new state, and go left or right. So present state, input, output, next state, and then this extra fifth component, move the tape left or right. And for us, we're moving the read-write head left or right because it's easier to draw on paper. And so let me make a let me see if I can make a sample Turing machine program that'll do something interesting. So we'll start in state S0, and if there's a 1, and how did I do this last week? Did I do, let me just pull it up. I'm trying to remember the order of the third and fourth arguments, but just so I'm not like swapping it on you. So, okay, so it was old state, input symbol, and then I did new state, output, and which way to move the read-write head. Alright, so I'll do my machine. If we're in state 0 and there's a 1, we're going to stay in S0. We're going to write a 0 and we're going to move left. If we're in state 0 and there's a 0, we're going to move to state 1. We're going to write a 1 and we're going to move left. If we're in state 1 and there's a 0, we're going to stay in state 1, write a 0 and move left. If we're in state 1 and there's a 1, we're going to stay in state 1, write a 1 and move left. If we're in state 1 and there's a blank, we're going to go to state 2, leave a blank and move right. And if we're in state 0 and there's a blank, let me see. We're going to go to state 2, we're going to write a 1, and we're going to move left. Alright, there's my obviously not quite random state machine. And I'm going to suppose that my tape is filled with blanks everywhere except for a little section in the middle that has 1s and 0s. And so suppose my tape contains, you know, a bunch of blanks. And then, I don't know, 0, 1, 0. And then a bunch of blanks afterwards. And suppose I'm starting off right here. And I start in state S0. That's my initial state. So, tell me what this machine does step by step. What's the first action it's going to take?
Input 0.
Okay, got an input of 0. And so what does it do?
Move to S1.
Okay. And how do you know that?
I'm just looking at the second row.
Okay, second row says if you're in state S0, which we are, and the input is 0, which we are, change to state S1. And then what else does it do?
It sets that bit to 1.
Sets that bit to 1.
And then moves left 1.
And then moves left 1. Alright, cool. Alright, what's the next thing that happens?
You're in state 1 and you see a 1, so you remain in state 1, leave that 1, and then move left.
Alright, so we're matching state 1 input of 1. That's this fourth instruction, which says stay in state 1, write a 1 to the tape, and move left. So now we go over here. What's the next thing?
So we're still in state 1. Input 0. And then we're still in state 1. So output 0. And then move left.
Alright, so we're matching this third one. We're in state 1. There's a 0, so we're going to stay in state 1. We're going to write a 0 on the tape, and we're going to move left. And what's the last thing it does?
And then this last one is basically going to end it, because you're in state 1, you see a blank. You're going to change to state 2, write a blank, and move right. And then we don't have any state 2 definitions.
Yep. So this last instruction matches state 1 blank. We go to state 2, we leave the blank there, we move to the right. And now when we try to find something which matches state 2 and a 0 in this case, there is no such state. We end up halting. And so the whole effect of this program was to change this input string into this input string. Okay, let's rerun the program. But let's just suppose our original input string was 0, 1, 1. and we're starting over here. And we start in state S0. Alright, S0 with a 1, we're going to stay in S0, we're going to write a 0, and we're going to move left. S0 and a 1, we're going to stay in S0, we're going to write a 0, and move left. S0 and a 0, we're going to change to S1, we're going to write a 1, and we're going to move left. And S1 with a blank, we're going to go to S2, we're going to move right, we're going to leave the blank here. And then S2 is going to halt our machine. So this took the string 011 and changed it into 100. So what is this machine doing to a binary string?
It kind of seems like it's just adding 1.
That's exactly what it's doing. It's doing addition. It's an increment circuit. And how does that work? Well, because when you add numbers with pencil and paper, how do we do this? If we have a 1 here, we're going to write down a 0 and we're going to have a carry. If we have a 1 here, we're going to write down a 0 and have a carry. If we have a 0, we're going to write down a 1, have no carry, and then we're just going to take the rest of these digits and copy them verbatim. So state S0 is where we start, and if we have a 1, we're going to write down that 0, and S0 means we've got a carry to deal with, right? We're ready to change 1s into 0s. So as long as we see 1s, we're going to replace them with 0s and keep moving to the left. But the first time that we encounter a 0, we'll toggle that to a 1. That's, adding that carry to the 0. And then we go to state S1, and S1 is just the state where we're just copying the input to the output. So 0s become 0, 1s becomes 1. And then when we get to a blank, we know we've hit the end of our number, and we just leave the blank there, and we're done. But if we're in state 0, and we add a 1, right, that gives us a carry of 1. If we move left and we've got a blank, we know that we've got an extra carry to deal with. We're going to have to write a 1. So in state 0, where we're rippling that first 1, if we find a blank, we'll go ahead and we'll write a 1. And then we'll go to our unknown state and halt the machine. So this is an increment program. It does I++, but with a little more work. Alright, let me try one more. So we're going to start in S0. And let me see. I think this works. So let's try this on a couple of strings. We're going to start sitting over here. We're going to be in state S0. So what does this do to the string 001?
Is it gonna decrement? No.
Could be something like decrementing. So what does it do in the beginning? Let's just look at a specific example first, and then we'll break it down more generally. So we're in state 0 and there's a 1. What's it gonna do?
Switch to state 1, right of 1, move left.
Switch to state 1, right of 1, go to the left. Alright, we're in state 1 and there's a 0. What's it gonna do?
Flip it and move left.
Flip it and move left. There's a 0. What's it gonna do? Flip it and move left. There's a blank. It's gonna halt the machine, basically. Alright, what about 1011? So we start in state
Right
0.
of 1.
State 0 and there's a 1. It's going to leave that 1, change to state 1.
And then it's gonna flip all the other bits.
It's going to flip all the other bits. So S1 has an interesting behavior. Once you're in state 1, if you see a 0, write a 1. If you see a 1, write a 0. If you see a blank, you're done. So this is going to come out to be 0101. So S1, toggle each bit from wherever you are out to the left. But what is S0 doing? If you've got a 0, go ahead.
Oh, it's just gonna keep writing zeros until it sees a 1, and then it's gonna flip state, so it'll just copy what it has until it sees a 1.
Mm-hmm. And that first one it sees also gets written. So S0, copy until first 1. So what this is doing is if you have a binary number, it's keeping everything up to and including the first one intact, and then it's toggling all the rest of it. Does anybody remember what that operation does? It's an Engineering 250 flashback. Keep everything up to and including the first one, and then toggle everything after that.
This isn't the complement, is it?
This is the choose complement. So if you think of your 3-bit numbers, right? So keep everything up to and including the first one, and then toggle everything. Well, there are no ones here, so let's just keep that. Here, this is the first one, and so we toggle everything else. Here we keep the 1, 0 and toggle everything else. Here we keep the first one and then toggle everything else. Here we keep everything up to and including the first one. Keep the first one, toggle everything else. Keep the first one, toggle everything else. Keep the first one, toggle everything else. And so this is 1, this is -1, this is 2, this is -2, this is 3, this is -3. This is actually -4 is -4. There's no +4 in 3-bit 2's complement. So this is a program that will generate 2's complement. So we can increment a number. We can negate a number. Could we make a Turing machine to add 2 binary numbers?
Probably.
Yeah, I mean, it might not be simple, but what do? If we have two zeros, then we put down a 0. If we have a 0, 1, we put down a 1. If we have two ones, we put down a 0, but we go to a different state, which represents the fact that we have a carry coming in. But this is significantly more challenging, because where are we going to store our two numbers on this piece of tape? If we could interleave them, if we could do, A3, B3, A2, B2, A1, B1, A0, B0, that might not be too bad. But, typically we'd have our numbers written side by side. And we need to decide where to put the output. Well, if we're incrementing or doing a 2's complement, we can just overwrite the original number. But to add two numbers together, I don't know where we would put the sum. Maybe we could overwrite this, or we could, put it at the end here. And so we start to get into a challenge of how do we move around this tape to pick off things from different places in the tape. And I want to just challenge you with one more example of that. So we did a program to increment, right? Something which would take us and change it into a 100, 110. And we did that, with the assumption that our read-write head was sitting over here on top of this rightmost digit. But suppose we didn't have that assumption. Suppose our read-write head could be sitting anywhere over this number. Can we write a program to move this head over the rightmost digit?
Yeah.
So we could do something like, if you're in state 0 and it's a 0, let's stay in state 0, write a 0 and move to the right. If you're in state 0 and there's a 1, stay in state 0, write a 1 and move to the right. And so these two states will just keep going troink, 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 troink until you get down to here. And then if you're in state 0 and there's a blank, now we go to like state 1, leave the blank and move to the left. Bingo. You're at the least significant digit of your number. And now, S1 would be where we'd start our increment program. Now suppose our read-write head was sitting somewhere over here in the middle of all of this blank tape, and we wanted to get it over to this least significant digit. Can we do that?
Yeah, you go basically state 0 or, state 0. If it's blank, then write a blank, or stay in state 0, write a blank, and then move left.
Mm-hmm.
And that would do that.
And then if it's state 0 and it's 0.
State 1.
And you could choose which way to go here. I might just go right, and if you're in state 0 and there's a 1, go to state 1, write a 1 and go right. And so this will move all the way over until it gets to this least significant digit. It will leave that digit intact, go to state 1, but then move over here. And so state 1 could say, if you're in state 1, we know it's a blank, go to state 2, leave a blank and go left. And now state 2, we know we're sitting over this least significant digit. And certainly if our read-write head started off over here on the left of all of this, we could write a similar program, which basically keeps moving right as long as it finds a blank, and then when it gets to a digit, does this thing to move to the right of the digits till it gets to another blank, and then moves left. So here's a question, and I'll take a break after I ask this and let you think about it for a few minutes. Suppose I know that somewhere on my tape I have a binary number, and it's got an infinite number of blanks on either side, and suppose I have no earthly idea where I am on the tape. How could I design an algorithm to move my read-write head so that it's right over that least significant digit without knowing where on the tape this number is. So let's do a 5-minute break, and if you want, you can think about that while you're stretching your legs or your brains or whatever, and we'll talk about it when we come back. So let's do a break until 14:03. All right, so I'll be back in a few minutes. Alrighty. So what we got? How do we do this?
Okay, so I thought about maybe like, because you don't know if you're to the left or to the right of the data, right?
Correct.
So you could, start in state 0, check to see the bit underneath the caret. If it's a blank, then move to the right, or rather, switch to we'll switch to state 1, write it blank, or maybe even just like a 1 actually.
So maybe don't think about it in terms of states. Let's just think about an algorithm from a higher level.
So I was thinking about like oscillating. So you would write a bit, move to the right, check that bit, and then move to the left until you found either a blank or a bit that was not the one that you wrote.
Mm-hmm.
Or at least the value that you wrote, right?
Yep. Cool.
And then you basically just keep switching between, just move back and forth until you hit, a bit that you did not, or that's a different value than you wrote, but, what if the input is completely made up of the value that we were writing?
Mm-hmm.
So,
that should do it.
Okay.
So did everybody catch that? So if you don't know where you are, right, if you know that you're to the right, you can just keep moving to the left. But if you happen to be sitting over here and you keep moving to the left, you're going to do that forever. So oscillate or alternate, right? Start off here, move 1 spot to the left, move 2 spots to the right, move 3 spots to the left, move 4 spots to the right, and keep going until you eventually hit a digit. Once you do, you know that you're at the number. And if you hit it going to the left, you know you're at the beginning. If you hit it going to the right, you know you're at the end, and so move over to the beginning. And so that's one way to find, this number in the middle of an infinite length of tape. Even if you have no idea where you are relative to the number, you can still find it in a finite number of steps. And that's kind of a different mindset from, for I equals 0 to 10, or while, character is not equal to blank, or something like that. But it's, it's another algorithm. And part of the challenge of a Turing machine is, we've got this tape that has our data we're manipulating, but this is also the same tape where our temporary variables are stored. And so how do we know, that we just moved 1 to the left, we should move 2 to the right? That kind of thing. Well, wherever we start, maybe we'll write an X on the tape, and we'll move to the left. And we'll write an X, and then we'll go to a state which says move until you find a blank. And at that point, write an X and move to the left until you find a blank. And at that point, write an X. And in addition to checking for a blank, you also check for this 1. And so, or this number. And so eventually you find a digit. Well, now you go into a temporary state which says, okay, I know that my number was to the left. Let's just look for X's, and as long as we find an X, let's erase it and move to the right. And then when you get to a blank over here, we'll go into a state that just moves us all the way to the left until we get to a non-blank, and now we know we're at this digit. And if instead we hit a digit when we were moving to the right, we do the same thing, but flip the steps. So you can start to rethink, how you write algorithms in terms of these different operations. And, this is kind of what we do when we move from one language to another. Usually, if we know C and we're trying to learn Python, it's not as big a leap as if we know C and we're trying to write a Turing machine program, right? This is about, this is one of the bigger leaps that we could make. But there are other esoteric programming languages that let you write programs with just a small number of instructions, or with strange instructions, or with just, counting white spaces or things like that. But it's all, kind of the same mental process of envisioning algorithms using different building blocks, basically. And so Turing machine was, one of the earlier sort of languages that people used. This was before we had, programmable computers in general, other than like, the difference engine that Ada was coding in the 1800s. So that's Turing machine work. And I think let me see the homework questions. Yeah, so for the homework questions, I don't need you to do all of this. You're welcome to start the tape, somewhere reasonable. So design a Turing machine that, given an arbitrary bit string, will append a single one to the rightmost end of the string. Well, don't just start it at the rightmost end, but, start it somewhere in the string and move to the right, basically. But no, you don't need to do this most general version of trying to find it, because that's kind of a whole big problem in itself. Given an arbitrary bit string, replace the first two consecutive ones with 0. So you could start that, at the rightmost part of the string. And first two consecutive ones, I had in mind that would be, first two as you're moving in this direction. But, you could do it either way. Just specify whatever assumptions you're making. And the goal here is just to sort of, kind of force you to get some experience writing these programs. So I'm not going to get too jiggy with them. So there's Turing machine simulators that you can get to. This is probably my favorite one. It has, a sort of infinite tape up here. There's the read-write head. On this machine, the read-write head actually moves rather than the tape. And you can have symbols on here, and you can load programs in. And this is, a little different from our simple programs of, 5 tuples, where it's just state input, state output, movement. These programs are embellished. So for one thing, they have comments, cough, cough, and they have some wildcards in them and things like that, and they have some labels and so on. So but it's still equivalent to a Turing machine program, so you could take this and turn it into something strictly like those 5 tuples that we've written. But we can load an example program. So let's do binary addition, and here's a pair of binary numbers, and we can say go ahead and run this program. So here's what the program looks like, and it's got 30 some steps. And we can run it, and you can see the head moving back and forth, and it's writing different values on here, and there's the final output. And so let's try something. So somebody give me an integer from, say, 0 to 31.
27.
27. Okay, and someone give me another integer.
23.
23. All right. So let's have this machine add 27 and 23. So 27 would be 16, 8. So I think it looks like that. And then 23 would be 16 and 7. And so if we add these together, we should get 50. And what is 50 in binary? 32, 16, 8, 4, 2, 1. So we should get 110010. And so let's see what this does. So there's our input values, and we'll go ahead and run. and it will highlight, you know, what step it's on as it goes through this. 110010. So there you go. And it took 107 steps. So, you know, pretty efficient. So here's binary multiplication. So let's, I should have written those down. So here's 27 and 23. Let's multiply those. And meanwhile, I'm going to calculate out. And I'll do 27 times 23, and I will put that into, I can put it into binary. So I should get 10011011101. And I'm going to have this thing run at full speed. There we go. Oh, that did not work. Did we just break computer science? Twenty-seven times 23. I'll run it again. There we go. All right. So 10011011101. I think I didn't load in the previous values. And it took 1,400 steps. So this can multiply, right? And it's a little harder than just saying y equals a times b. It's, you know, over 100 steps. But you can see it's throwing down, you know, temporary markers to keep track of where it is, and whether there's a carry to be generated, and so on and so forth. And it's also producing the output alongside the inputs. But it needs to keep the inputs, at least one of the multiplicands, at each step, because it has to repeatedly add that and multiply it by another digit of the other multiplicand, and so on. But this works. So it's not a 215 class if we don't do primes. So let's do a primality tester, and let's see if 5 is a prime number. So we'll run this at full speed. And so it's decided 5 is a prime number, and it took 1,500 steps. And let's try 7. And it took 2,600 steps and found 7 is a prime. And let's try 9. And so this is doing, you know, repeated division. And after 3,300 steps, it found out that 9 is not a prime. Presumably it found it was divisible by 3. So we'll just try 31 while we talk. So, you know, how do you write something like this? This is a longer program. It's a few hundred steps. But you write it in pieces, right? So what do you have to do? You have to be able to divide one number by another. And how do you do that? Well, you do repeated subtraction maybe, which means you need to be able to subtract. And you need to be able to generate successive possible factors, so you have to be able to increment something by 2. And you need to be able to compare two numbers to know if you're bigger than the largest divisor you have to test. But you know, you write these things in pieces, and you know, you leave the machine to do the work. So I don't remember how many steps this takes. I think it takes like 10 minutes or something to conclude that 31 is prime, because it's got multiple divisors to test. But it's really, you know, fundamentally no different from writing in C or Bash or Python or Java or assembly language. It's a different set of building blocks. And so this was you know, the model of computation that was used in the 20s and the 30s to explore some of the early questions about computability and what computers can do, and so on. Alright, so 4,500 steps, and I found out that 31 is prime. So that's pretty cool. And then this should be pretty quickly composite, because this is 33. So these Turing machines have been studied for some time, so I'll just, oh, I think it finished. Nope. I'll just leave this in the background. See here. And so these are a particular type of Turing machine called a deterministic Turing machine. Or a DTM, or sometimes just a TM. Normally when we say Turing machine, we mean a deterministic Turing machine. And the sense in which it's deterministic is that for each state and input, there's a specific next state that we're going to go into. If we're in S0 and there's a 0, we are going to go to state S1. If we're in S1 and there's a 0, we're going to go to S1. If we're in S1 and there's a blank, we're going to go to S2. Hey, it found 33 is not prime. 3,400 steps. All right, so this is a deterministic, or kind of a plain old Turing machine. But there's another kind of Turing machine. This is a theoretical one called a non-deterministic Turing machine, NDTM. All right, a non-deterministic Turing machine is a Turing machine with a little genie inside. And this genie is really friendly. And the genie does the following. In the program for a non-deterministic Turing machine, it may be that we have statements for, say, if you're in state S0 and your input is a 0, go to either state 1, 7, 12, or 29. We might list multiple possible next states. So a deterministic machine, current state and input completely determines your new state. A non-deterministic Turing machine, you might have multiple next states. So imagine writing a C program which says, you know, if x equals 0, either do this, do that, or do this other thing. And the machine gets to choose which of these three things it's going to do. That would be like a non-deterministic C program. And, you know, on a good day, that's not something that happens. But it does happen sometimes, right, when you overflow an array or something. So a non-deterministic Turing machine deliberately has ambiguity. There's a possibility that for a certain state and input combination, there could be different next states you could go to. And the decision of which next state to go to, we can think of as being made by a friendly little genie that sits inside the machine. And the genie is very happy when it can help you solve your problem quickly. And so now we take a problem we want to solve and we think of it in terms of, you know, if you could write an if statement with multiple then clauses, and something in the machine could decide which then clause to execute first in such a way that we would get an answer to our problem. So for example, if I wanted to know if a number is prime, instead of saying let's divide by 3 and then 5 and then 7 and then 9 and so on, I could say, okay, let's divide by either 3 or 5 or 7 or 9 or 11, you know, or some number, and I would let this genie decide which number am I going to divide by first. And the genie might be, you know, kind enough to say, you know, oh, you want to see if 1001 is prime? Okay, we're going to try dividing by 7 first. Hey, it's divisible by 7. We're done. It's not prime. Okay, this is not a real thing. This is a theoretical version of a Turing machine, but it is possibly not totally unlike something like what we get with quantum computing. It's another subject. So imagine a non-deterministic Turing machine. This is much more powerful. There are problems that are very hard to solve on a real Turing machine, a Pentium processor, for example, that could be solved very quickly with a non-deterministic Turing machine. And in particular, if we can take our question and change it into a yes-no question, where the machine is simply trying to give us a yes or no answer, we may be able to construct a program on an NDTM that will very quickly give us our answer. Alright, so what does this have to do with anything? This is related to theories of computation and questions of, you know, how efficiently we can solve certain problems. So we know about order of complexity, right? We know that some problems are linear, some problems are quadratic, some problems are logarithmic, some problems are horrifyingly slow, some hash table operations are delightfully fast. And we're particularly interested in this order of complexity, and not just n squared, but, you know, order n cubed, order n to the 7th plus, you know, 5n squared. These orders of complexity where the expression in here is a polynomial. These are particularly common. And so bubble sort is an order n squared algorithm. Matrix multiplication is an order n cubed operation, I believe. So, you know, 222, we know the logarithm is really nice. We know n is pretty nice. We know 1 is really, really nice. We generally say n squared, not so good. Bubble sort, no. Merge sort, yeah, that's good. But there are things worse than n squared or n cubed or n to the 7th. There's things like this, or there's things like n to the n. And these are really, really inefficient. So these problems that have an order whose expression can be written as a polynomial, and remember, this is not a polynomial. Polynomials are integer powers of n multiplied by coefficients added together. N to the 1,000th would still be a polynomial expression, but n to the n is not. It's bigger than any polynomial. And so here's a classic question. Can a given problem be solved by an algorithm with order some p where p is a polynomial? So sorting, we know we can solve. Well, we can do better than polynomial, but we can certainly solve, you know, a sort problem with order n squared. You know, finding the smallest element in an array is an order n operation. So n is a polynomial. It's n to the 1st. Multiplying matrices, n cubed. You know, finding the smallest, finding the matrix with the smallest determinant if you've done 215. smallest determinant from a set of n matrices, right? That's a polynomial, but a large polynomial. And so in studying questions of computation, we break down problems into different categories. And we say an algorithm belongs to class P if it's solvable in polynomial time on a Turing machine. Turing machine, you can think of, Pentium processor running C or something. So if we can solve an algorithm in polynomial time, that algorithm belongs to class P. And there's lots of algorithms that fall into class P. All the stuff we've done that's order n squared or n cubed, those fall into class P. Anything that's order n, that falls into class P. Heapifying is class P because that's order n. If you did 222 today, or we'll do it tomorrow. But there are some algorithms that take more than polynomial time. And so one example, I mean, we've done some with some of our recursive algorithms. A knapsack problem takes more than a polynomial amount of time. Rod cutting, egg dropping, longest common subsequence, these things take more than a polynomial amount of time, perhaps. So traveling salesperson is sort of the classic problem. And so picture, a map where you have roads between cities. And each road has a certain distance associated with it. Obviously, I did not get my map drawing badge. All right, there we go. And so, there's distances or times or some sort of weights associated with each of these lines. And the goal of TS, yeah, that's where this is leading. The goal of TS is, starting with one start point, you want to travel to every city and come back to the beginning with as little distance traveled as possible. So let me do a simpler map here. So we want to start from city A, visit cities B, C, and D in no particular order, and come back to A. And we want to minimize our travel distance. And I could clearly go from A to B to C to D and back to A, and my distance would be 10, 25, 36, 41. But I may do better to go from A to C, that's 7. C to D is 11, D to B is 2, and then B to A is 10. That turns out to be a distance of 30, so that's a shorter distance. Or I may go A to D, which is 5, and then D to B, which is 2, and then B to C, which is 15, and then C back to A is 7, and I think that ends up being 27. That's an even better solution. And you can visit a city more than once if that's really useful. Maybe there's one path to C that's inexpensive and all the other paths are really expensive, and so it's quicker after you visit C to come back to B and then go somewhere else. And so the traveling salesperson question is, given a graph, right, a set of connections with distances between them and a starting and ending city, what's the best order in which to visit these cities in order to minimize your total travel distance? This is a very old problem, and it's a very well-researched problem. In fact, it's probably one of the most explored problems by sort of hobbyist computer scientists and mathematicians to try to come up with an algorithm to solve this question. And all the algorithms that we've come up with for running this on, you know, say a Pentium, tend to be much worse than polynomial time. Now, it's a simple thing to do, right? We could simply explore every possible path through this graph and just record what the shortest path is. And if you have a total of n cities, well, from my first city, I have how many places I can go. I have n minus 1 choices I can make. And from this city, let's suppose I don't go back to a city I've already visited, I have n minus 2 choices to make. And then from the next city, I have n minus 3, and so on. And so this looks like order n factorial. And if I allow myself to go back to other cities, then at each point I have n minus 1 options to choose from. And if I suppose I'm going to go through, I don't know, let's just say n cities, right? This might be order n to the n. But, you know, certainly worse than, say, you know, n squared or n cubed or even n to the 1000th, right? If I pick a big enough n to the n is eventually bigger than any polynomial. N factorial is eventually bigger than any polynomial containing n. And so these are fundamentally worse computation times. So we would like to know if there's a way to solve traveling salesperson in polynomial time. In other words, is traveling salesperson a class P problem? And we don't have an answer to that. Alright, but here's what we do know, and this is where it gets really interesting and really kind of freaky. There's a second class of problems called NP. And an NP problem is solvable in polynomial time on a non-deterministic Turing machine. So NP does not stand for not P, it stands for P on a non-deterministic Turing machine. In other words, if we had this genie and if we had, you know, a multitude of states we could go to, we could find a polytime solution to traveling salesperson if it's class NP. Alright, so we got two classes of problems. We've got class P, which are the problems that aren't too bad to solve. We've got class NP, which are ones that we could solve in polytime given this you know, fancier Turing machine, the non-deterministic Turing machine. But there's another class of problems which we call NP complete. And the idea of NP complete is if a problem is in this class and we can solve that problem in polytime, we could solve every problem in this class in polynomial time. So an NP complete problem is a problem that is solvable in polytime on a non-deterministic Turing machine. But it's got this extra characteristic that if we could find a way to solve this in polytime on a plain Turing machine, we could solve every problem in this class in polytime on a plain Turing machine. Or one way to think of it is that we could take a solution for solving this in polytime and change it into a solution for solving any other problem in this class in polynomial time. And traveling salesperson is an NP complete problem. And so what all of that means is that if you find a way to solve traveling salesperson in polynomial time on a plain Turing machine, there are a whole bunch of other questions that are really hard to solve today that we could suddenly solve in polynomial time. So finding a polytime solution to TS has become a big quest for a lot of people. And it's one of these things that there's, you know, like $1 million prizes out there if you come up with a solution. And mathematics journals, computer science journals are periodically flooded by, you know, submissions from people claiming that they found a way to solve traveling salesperson in poly time. And inevitably these solutions have had problems to them. They have not been what they thought they were. And so let me show you a list. This is from Wikipedia. Here's a list of NP-complete problems. So these are problems that if you can solve traveling salesperson in poly time, you can solve all of these. So there's some graph theory questions. We haven't talked about graph theory yet. We'll cover that in 223. Some mathematical programming, three-partition bin packing, knapsack problem, variants of the knapsack problem, traveling salesperson problem, bottleneck traveling salesperson, all these weird things. Subset sum problem, that's another good dynamic programming example. All of these things that are hard to solve in poly time would suddenly be doable. String processing, shortest common subsequence, longest common subsequence. Bunch of games, Battleship, Bejeweled, Candy Crush Saga, I think Pokemon's in here, Pokemon. Legend of Zelda, right? Super Mario Brothers, now you know it's good. And other problems, map coloring problems, all kinds of weird things, right? And all these problems are solvable in poly time on a non-deterministic Turing machine. And if any one of these, if somebody discovers a poly time algorithm for solving any one of these, that will lead to a poly time solution for solving all of these. This is the magic of the PNP question, right? If you can solve any one of these in poly time, you can suddenly solve all of these in poly time. And that's a huge win for the day, right? If you come up with a solution to traveling salesperson that's, you know, order n to the 10 millionth, you've just solved the PNP problem, and you've got a poly solution for all these questions. And that's one of those things that like changes the world overnight. That's like a singularity-inducing event. And the next day, you know, you can sort your pancakes. And the jury is split on whether people think this is going to happen or not. So you'll see this, you know, on websites or in the literature as this: does P equal NP? Is a set of poly problems the same as a set of non-deterministic poly problems? And some people believe it is, and we just haven't found it. Some people believe it's fundamentally not. So it's an open question in the theory of computation. Now there's other questions. There's these NP hard questions, which are so complex that even if P and NP turn out to be the same thing, these still can't be solved in poly time on a traditional Turing machine. They're harder than the NP complete problems. But this is really the interesting question a lot of people are asking is P and NP. All right, so let's that's a question of, you know, order of complexity. How quickly can we calculate things? But even more fundamental question is, you know, what can be computed, or what can be computer if you can't type. So what sorts of things can we compute? And, you know, we saw a homework question, can you write a program that tells if you input the same number of ones and zeros? And the answer is no. I mean, you can up to a point, but in the general case, no. There's not enough memory in a finite state machine. But there's other interesting questions. And one of these is called the halting problem. So here's the halting problem. You're going to write a function called halts. And it takes two inputs. It takes a program, let's say it's written in C, and it takes a set of input. If that program ingests any input, here's a copy of the input you're going to feed to it. And halts returns an integer. And your halts function returns a 1 or a 0, indicating whether this program run with this input will eventually exit. So does this program eventually, you know, terminate and you go back to the operating system, or does it run forever? So, you know, our programs don't halt, but they exit, so I'll say halt. But think of just, you know, like hitting a final return. So you want to write a function that can take, for example, a C program and a set of input, analyze the program and tell you, hey, that program eventually exit, or that program runs forever. And the question is, can you write this function? Would this be a reasonable programming assignment to ask you to come up with? Assuming this class was like, you know, 25 years long and you had lots of time. And if you think about, you know, how you would solve this, well, what do some C programs look like, right? Integer I equals 0 while I is less than 10, I plus plus. Return. Well, we can look at this program and we could probably all say, you know, this program will exit. It'll set I to 0. While I is less than 10, it will increment it. This loop will run 10 times. Eventually, I gets to be 10. We leave the loop. We return. So we could look at this and we could say, yeah, this program will exit. No problem. And if you write while loops the way I do and you forget to do this I++, you can look at this and say, hey, this program will never exit. It's going to run forever. And if you do something like, you know, sum equals 0, sum plus equals I, if sum percent 7, increment I, will that eventually exit or not? So I'm going to keep adding consecutive integers to a running sum, and if my sum is divisible by 7, then I'm going to increment I. And so will I encounter 10 numbers where sum is divisible by 7? I don't know, but you could think about this and play around with it and do some modular arithmetic and probably conclude, yeah, this program will eventually exit. So the goal is to be able to write a program that will do this for any input program and any set of input to that program. And it would be hard. You'd need to have a program that can understand C code. But, you know, we have programs that can do that. They're called compilers. We have emulators that can do that. But you need to somehow, you know, study the structure of the program and look at what's happening. And we can do this for some examples ourselves, but can we write a program to do this? And one requirement is, you know, must give an answer in a finite amount of time. If it takes 100 years, that's okay. But it has to eventually give an answer. If my halts function runs forever in some cases, it's not a valid solution to the halting problem. And so intuition, gut feeling, top of your head idea, is it possible to write such a function, do you think? Something that could analyze a C program and a set of input and tell you whether or not that program will eventually exit.
I mean, you could at least look for common pitfalls that would create, in short, no, but in my opinion, but you could, look for, like, the common,
Yeah.
type situations, but yeah, I think it'd be too difficult to try and think, or at least take into account every possible way of creating an loop.
Yeah. I mean, it's there's certainly some cases. If you have a while, condition, you put a semicolon at the end, which is a pretty common bug, by the way. That's an infinite loop, right? There's nothing in the body of the while statement, and so unless this condition is false the first time, this is going to run forever. And if you have a return statement and you can see that some combination of inputs will get you to that return statement, you could say, yeah, the program will exit. But it's a tricky thing to try to imagine how to do this in absolute generality. And it's not sufficient to just simulate the program, because if the program never exits, your simulation would never end and you wouldn't give an answer in a finite amount of time. You would simply never give an answer, but that's not the same as saying the program runs forever. On the other hand, as computer scientists, if someone ever tells you there's a program that you cannot write, that should at least annoy you. Or rather, let me just say, it annoyed me, right, when someone told me this a long time ago. Because, why am I studying computer science if there's, like, limits to what I can compute? So this is a form of the question that Alan Turing was studying in the 1920s, for which, among other things, the Turing machine was conceived of as a model of computation. And this was a variant of one of David Hilbert's problems. So we talked about Hilbert in the very beginning of the course with Hilbert's Grand Hotel. Same guy. So one of his questions was related to algorithms that can analyze themselves, and an equivalent version of that is the halting problem. And so Alan Turing was trying to study that question. And the conclusion of Alan Turing's analysis was you cannot write this function. It's impossible to write a function that will tell you whether or not a program will halt in all cases. It might work in some cases, but to write a program that will analyze any program and give you a definitive answer is allegedly impossible. And the reason for it, if we're willing to wave our hands, is pretty simple. So suppose you've got a function that will do this. You come to me and you say, hey Nick, I've solved the halting problem, here's my function. And you hand me a flash drive and it's got a big C program on it. And it's a function called halt. It takes a program and a set of input and it returns a 1 or a 0. Right? And remember, 1 means it halts, 0 means it runs forever. And it has to give me an answer in a finite amount of time. So somewhere in here, right, you have a comment, because of course you comment your code, and your comment says, program halts. And so you return 1. And somewhere else in here you have a comment where you've discovered that your program runs forever. And so you return a 0. And you've probably got other stuff in here, and there's an ending curly bracket. And you got other functions and stuff like that. But, you know, ultimately somewhere, there's got to be somewhere where the program returns a 1 because it says your program will halt, or where it returns a 0 because it says it runs forever. All right, so here's what you do. You take this program and you tweak it a little bit. You take this program and right here before it says, you know, return 1, you put in an infinite loop while 1 equals 1 semicolon. And down here where it says, you know, program runs forever, you put in an exit statement. And now you run this program on itself. And you say, okay, tell me whether you're going to run forever or you're going to exit. And if this program really solves the halting problem, it will analyze itself, and it will eventually come to a conclusion, because it has to respond in a finite amount of time. And there's two possibilities. It may conclude that the program halts, at which point the program goes into an infinite loop and does not halt. And so if it predicts the program's going to halt, it gave an incorrect prediction. And if it predicts that the program is going to run forever, it goes ahead and exits. And again, it's given an incorrect prediction. And this is a diagonalization argument. This is how we showed that there's more than a countable number of real numbers. This is taking something which is supposed to solve a problem and using it against itself. And so a version of this can be formalized and basically tells you you cannot write a program that solves the halting problem. And that's generally accepted to be the truth. I have my own opinion about it. But that's the textbook answer to the halting question is no, you cannot write a program that will analyze another program and tell you if it halts. And this was done in the language of Turing machines. So it was trying to come up with a Turing machine program that if you had a tape containing a program for a Turing machine and instead of input, can you analyze that machine and conclude whether it's going to halt or not? And the answer is no, you cannot. And that feels like the right answer, even if it is annoying to be told there's things your computer can't do. It feels like the right answer because if you could solve the halting problem, think of the things you could do. So for example, you did an assignment with Goldbach's conjecture. So we could write a program called, Goldbach.c and, test Goldbach's conjecture on consecutive even numbers. And if you can't write n as the sum of two primes, let's have our program exit. Right, so n equals 4. Try to do n as the sum of two primes. If you can, right, increment it by 2 and go back up and try the next number. So this is kind of like, a small modification on the program you already wrote for this class. So just keep generating even numbers and try to write each one as a sum of two primes. And if you ever get to a point where you cannot write your number as a sum of two primes, just exit. Otherwise, just keep going. Well, if you had a program that could solve the halting problem, all you have to do is take this C program, hand it to your halting analyzer, and say, does this program ever halt? And if that program comes back and says, this program never halts, we've just proven Goldbach's conjecture. Because if there was an even number that couldn't be written as a sum of two primes, this program would exit at that point. And if the analyzer comes back and says, yeah, eventually this program will halt, then we know there's a counterexample to Goldbach's conjecture, because the only way this halts is if we eventually get to a number that can't be written as a sum of two primes. And so we could start taking all kinds of problems and thinking of them as variations on the halting problem. And we could use the halting problem as kind of, you know, a different kind of genie that could tell us all sorts of things about open questions. And we simply have to phrase our questions in terms of writing a program that, you know, runs forever in one case and halts in another case. And then it asks the halting program to tell us, does this program stop or not? So halting problem is considered unsolvable. You cannot write a program to answer that question. All right. That's pretty much as far as I was planning to go for 215 this quarter. Questions about any of that stuff?
I mean, you kind of broke my head there, but
That's good.
um, but yeah, no questions.
So the main thing we did not get to this quarter for this course was graph theory. And so I'm planning to go through some graph theory in 223 because that's a good place for it anyway. So we'll get to graph theory up to and including something called Dijkstra's algorithm, which is a way to find the shortest path through a graph, and that'll be useful in other courses down the road. So we'll do you know, topics from discrete structures throughout 223, and you'll do this throughout other courses too. But other than that, I think we've gone through everything that was in sort of the initial list of topics to cover. All right. Well, I'm going to let you out a few minutes early today, and I'm going to ask you to please bring questions to class on Wednesday. So I'm not planning to do any new material on Wednesday. So I'll spend that class basically going over, you know, a quick review of what we've covered this quarter, and saying a few things about the final exam. But that's going to be really boring and/or really short unless you have questions. So ideally, you know, we can spend Wednesday going over topics that you want clarification on. If you go back through your homeworks and there's things on there that you're not sure about, or any of the more recent material that you want to go over, right, that's how we should ideally spend our last class on Wednesday. Otherwise, like I say, I'll just kind of go through topics and say a few things about the exam, and it won't be terribly interesting probably. So some questions, plan to interact as much as you need on Wednesday, and that'll pretty much do us for the whole course. I still have office hours tomorrow morning and Friday, and that's it. That'll be it until spring quarter starts. So any other questions, right, you can always come to office hours for that too. Tomorrow's probably going to be pretty crazy for office hours, but we'll see. Sorry, Tuesday. I'm ahead of myself. Tuesday, Thursday, Friday, office hours. So you got 5 hours left. All right, any other questions, comments? All right, you got out 7 minutes early today. So enjoy the weather. It's like 50 degrees and sunny out there. Have a good one. I will see everybody next time.
Have a good afternoon.
Thank you.
Thanks.